শালগঙ্গাতে যেটা হইব ওইটার লেগে আপনি নতুন ফাইবারটা পর্যন্ত টেস্ট করে দিয়ে গেছে একটা, আর এটা মানে পেজ কোড লাগতে পারে, কনভার্টার লয়ে দিবা, এসএপি লয়ে দিবা।
So are you still admitting people?
Yes, sir, you can start.
We can start?
Yes, sir, yes, sir, start.
Okay, so let's move on. So it's about the basics of memristors and memristive devices. And as you can see, there's lots of interest in the world. Nature Electronics, a few different issues address memristors and CMOS, or 3D memristors. Also, it talks about computing in memory and the AI chips, etc. So there's lots of interest in memristor related to AI. Now, back in 1971, in IEEE transactions on circuit theory, that was the name of transaction before circuit and systems, circuit theory, back in 1971. Leon Chua, he published a paper on memristor as the missing circuit element. As you know, we have a resistor, inductor, capacitor, RLC element. And in 1971 paper, Professor Chua said that there is a fourth basic element, namely memristor. And he was linking what was supposed to be missing link between the charge as an integration of a current and the flux linkage as integration of a voltage. So it was a defining relationship between electric charge Q and the flux linkage phi. So that was his paper in 1971. And then the next year, I joined Professor Chua's group, and we worked on generalization of what's so-called ideal memristor, and they introduced the concept on memristive devices and the systems. And that was published in February 1976. So that, if you look at the equation number 2, it has a Ohm's law. Voltage is equal to resistance multiplied by current. It's Ohm's law. But that resistance is not constant anymore. It's a function of a state variable x, or can be function of a current, or can be function of a t. So R in general is a function of a state variable x, input current I, or time varying t. And then state variable itself, x dot, is a function of x, I, and t. So that is sort of a current controlled memristor. Current controlled memristor because the current is controlling a state variable, etc. You can also think about voltage controlled memristor, where you have I is equal to conductance multiplied by voltage, where conductance itself is a function of a state variable x, input voltage V, and the time t. And the state variable itself, x dot, is a function of x, V, and the t. So that was a generalized memristor. It's called, at that time, it called the memristive device characteristics, right? And if you indeed look into very world famous, the Hodgkin-Huxley model shown in this circuit diagram here, this is the membrane's outer wall and the inner wall. If you apply membrane voltage here, there will be current flowing through the membrane wall, has different components, a leakage component, sodium channel current, potassium channel current, and then also the capacitor between the external wall and the internal wall of a membrane. So that's the membrane capacitance, sodium channel, potassium channel, and the leakage channel. There's echo. Can you hear me? Hello?
Sir, we can hear you clearly. Yes, sir. Yes, sir.
It's okay.
Yes.
All right. So this is very important. Actually, it's related to the neuromorphic computing, because when we talk about neuron, which generates action potential, neuronal signal, one of the model popularly used is a Hodgkin-Huxley model. Actually, for this model, they got Nobel Prize. They are physiologists. But after publishing this model, and sometime later, they got Nobel Prize for this particular model. So this is a very famous model. Back in 1976 paper, we identified the two memristors in this model, sodium channel and potassium channel. If you look into the relationship between, for instance, the potassium channel case, potassium channel current and the potassium channel voltage here, say this is here, voltage across this, this conductor here, is expressed as IK is equal to GK n raised to the power of 4, fourth power, dk. So you can say that this is a conductance, a function of n. N itself is a state variable. N dot is equal to this complex nonlinear equation multiplied by 1 minus n minus 0.125 exponential function of Vk plus Ek, which is a biasing DC voltage divided by 80 multiplied by n. So this is a nonlinear differential equation, see? So that's why this can be declared as a memristor, for instance. If you look at the sodium channel, INA, sodium current, is equal to some constant, m raised to the power of 3 multiplied by h, and VNA. So this is a conductance is a function of two state variables, m and h, multiplied by VNA. So this is a conductance. And the m is described by this nonlinear differential equation. H is also described by this nonlinear differential equation. So in this case, there is 3 variables, n, m, and h. So 3 state variable in this nonlinear differential equation system. That's what Hodgkin-Huxley model is about. It turns out that it's always in a power of 4, n raised to the power of 4. Here is M3H1. So if you add 3 and 1 is 4. So they postulated that maybe you will have a conduction in each channel when 4 particles line up with a probability of 1. So then if they line up with a probability of 1, then it's a perfect conductance, GK, fully. But this N itself can be variable, ranging between 0 and 1. When it's 0, then there's no conductance. When N is equal to 0.1, 0.2, 0.3, toward 1, then conductance is going to increase. So, but it's always a power of 4. In this model, it's m cube h1. So 3 over m, 3 of them, followed by another h. So when they line up perfectly with the probability of 1, then you have a full conduction. But if any one of is 0, then there is no conduction. So state variable is controlling the conductance, G and A. Likewise here, state variable N is controlling conductance K. This turned out to be very complex, stiff nonlinear differential equation, but it can generate what is called action potential, which you will see later on. So back in 1976 paper, we identified ionic system as a memristive system, actually. So that was a very revealing experience at the time. That was way before neuromorphic computing concept came about. Now, this slide shows various aspects related to Memristor. So it describes materials systems, structure to build a device, the performance, performance of such a device, and then application of such a device. Do I have to push all this admit? Or can you do it over there? Yeah, so it's application either in logic operation or analog computation, like a neuromorphic computing type of thing. So we will see that there is a MAC operation, multiply accumulate operation, which is like an analog version of a matrix multiplication. So it has a nice application relevant to neuromorphic computing, right? There is also many books written about Memristor. One of the books is what is called the nonlinear circuits and systems with Memristors by the Torino, Politecnico di Torino, Professor Fernando Corinto, former PhD student Moro Forti, and Leon Chua, published in year 2020. It explains the Memristor circuits and the analysis in terms of flux and charge. So it's the first book of its kind. Now I am borrowing some slide from Professor Leon Chua's lecture, 10 things about Memristor. So he explains in his tutorial about the 4 basic circuit variables. That is voltage, current. We are very familiar with it. We are also familiar with the charge as an integration of a current, right? So the electric charge is a time integration of a current, minus infinity to t, I tau, d tau, that's qt. Flux linkage is a time integration of, voltage. Vt is equal to integration from minus infinity to t, v tau, d tau. So we have 4 variables, right? And then you can see in the next slide, voltage current relationship is defined by a resistor, Ohm's law, and current flux relationship, V is equal to Li, inductance relationship, voltage and the charge relationship, Q is equal to CV, capacitor times voltage. So that's well defined. All these H, 3 H's are defined. But question is, what about between Q and V? So this is what Leon Chua called as a missing link. There must be, by symmetry, some relationship, but nobody has defined this relationship. So this shows all these 4 basic elements. This square and then on the bar here means a nonlinear. So in general, there is a nonlinear resistor, linear resistor, but yeah, you have a resistor, you have an inductor, you have a capacitor. Now you have a memristor that filling the missing link. And then after that, the inductance was introduced, and mem capacitance was also introduced. So memory inductance, memory capacitance was introduced. So those are the recent, besides RLC, with the introduction of a memristor, you have a memristor, memory inductance, and the memory capacitance. So those three new elements came about after introduction of a memristor. And this is what is called the Gedanken experiment. So if you have an element, you keep measuring voltage and current at different time, and you can have a set of measurements, V1, I1, V2, I2, etc. So this is a set. And in principle, this set, FD completely characterized the behavior of this device in the sense that given any excitation VT or given excitation IT and the initial condition T naught, initial time, the corresponding IT or VT can be retrieved via this measurement set. In other words, this FD set acts as an analog memory bank, thus a lookup table containing the results of all possible experiments on a device D. So that's what is called the Gedanken experiment. So now this is a recap. You have 4 basic circuit elements: resistor between voltage and the current, inductor between current and the flux, and capacitor between voltage and the charge. Now this missing link is a memristor here. And to make it general, you include nonlinear memristor, nonlinear resistor, nonlinear capacitor, nonlinear inductor, nonlinear memristor. And again, the relationship between current and the charge is through integration. So if you integrate the current, you get a charge. If you differentiate the charge, you get a current. Likewise, between voltage and the flux, you integrate, you get the flux. You take a derivative, you get the voltage. Right? So that's the relationship. So this is a further explanation of a memristor, as discussed in 1971 paper by my advisor Leon Chua. And he described that it's a voltage current relationship. And if it's a nonlinear, it's a single curve passing through origin. So if it's a linear straight line, but it's a nonlinear, it would be curved like this. Now, when you have this voltage current relationship of a capacitor, it will have like a elliptic shape, Lissage figure. It's an elliptic shape. Elliptic figure, right? And likewise, if you have a voltage current Lissage figure, it also has an elliptic figure. What is different for the case of a memristor is it passes through origin here, just like a resistor here. So whenever input is 0, output is 0. So it must pass through origin. But it has a memory effect, some hysteresis. That's a memristor. So, the voltage current. So in this portion, right, compared to this portion, current is smaller. So this means when you are in this state, in this portion, resistance is high. So high resistance region. When you are in this region, resistance is lower. So it's highly conductive and lowly conductive. So again, here is the resistance is high, what is called a high resistance state. Here is a low resistance state, LRS state. And then there can be change of state. If you drive up, say, voltage here, follow this curve. And then if you exceed this, what is called the set voltage, then it will follow this curve. And if you decrease, it will follow this curve. And if you try to increase more, then it suddenly changes to this curve. So you can circulate this Lissajous figure, for instance. So again, a distinctive feature of a memristor is a missing link between charge and the flux. It pinched the hysteric loops in voltage current dynamics, right? It's pinched, it's at the origin. Has a capability of a resistor, right? Because it's following Ohm's law. Whenever input is 0, output is 0. Ohm's law. But it has a memory effect. So it's called memory resistor, thus memristor. Memristor, right? Memristor. So in ideal memristor case here, V is equal to R times I, but its state variable is Q, where dq dt is equal to I. So that's what is called the ideal memristor. If you generalize memristor, the resistance is a state variable X, and it can be also a function of I. So this is Ohm's law, but the X is a state variable, it's a function of X and I. So this is a generalized memristor, as published in 1976 paper. So in terms of basic circuit elements, again, capacitor, von Kleist, Georg von Kleist, 1975, defined the capacitor. 1981, Humphrey Davy, Leon gave him credit for identifying memristor actually. So Vt is equal to Rx I, where X is a state variable, dx dt is a function of Xi. So it can trace back as early as 1801. There are many historical evidence, so we will look at some of them. In terms of a resistor, Ohm's law, 1827. In terms of an inductor, Michael Faraday inductor, 1831. So, going back, 1745, capacitor. 1827, resistor. 1831, inductor. But then there was a Humphrey Davis definition of the memristor characteristics. He didn't call memristor, but it can be traced back. So this shows more about memristor relationship. Again, we said when I heard the first lecture by Leon Chua back in 1972, he called this a tetrahedron. So you can see that it's a three-dimensional tetrahedron. So you can see from the front side, you have a voltage and the current, familiar with the flux linkage and the charge. So you have a very clear edges, right? Voltage, current is Ohm's law. Voltage and the charge is a capacitor. The flux and the current is an inductor. And the voltage and the flux is a derivative or integration relationship. Charge and the current is a derivative relationship or integration relationship. But this is what is hidden behind of tetrahedron. So that has been behind. So Leon said, well, if there is a relationship, maybe phi is a function of Q, in general, nonlinear function, but you cannot make any sense out of it. We are so familiar with the voltage and the current always. So, but on the other hand, voltage is a derivative of phi. So if you take a derivative on the left-hand side, you have a d phi dt, which is v. On the right-hand side, if you take a time derivative, d phi q dt, then you can rewrite as a d phi q dq, dq dt, but dq dt is I. So this is a sort of slope information, which is a memristance as a function of q. So this is V is equal to memristance multiplied by current, but memristor is a function of Q, memory effect. So that's the memristance and the memristor definition, right? Now, I gave a lecture in one of the meetings in year 2011, International Joint Conference on Neural Network. It's called IJCNN. This July it will be held in Rome, Italy. I'll be there. But there, the Bernard Widrow, very well-known professor in signal processing from Stanford, came to meet me with this device here. See, it has a 1, 2, 3, 4, 1, 2, 3, 4, 4x4 system here. 16. It turns out to be they are tubes, chemical tubes, with some meter. He came with this one. It turns out that Bernard Widrow, he named this device, this tube, chemical tube, as a Memristor. Yeah. So, okay. So let me go back. So he called it Memristor, but it was not Memristor. So he called it Memristor. It's the same idea. Memory resistor, but he called it Memristor, but it was a 3-terminal device, 3-terminal, which is different from Chua's 2-terminal memristor as a basic circuit element. So that's a major difference. It's a 3-terminal versus 2-terminal. But he applied this one in a neural network exercise. So he demonstrated what is called the Adaline. It's a neural network system made in early 1960s with his PhD student Ted Hoff for neural network training. So Widrow, Hoff is well known, least mean square algorithm was implemented in this system. So thereafter, Intel was very interested in this concept. They hired Ted Hoff, tried to fabricate memristor in solid state, 3-terminal solid state. They couldn't. Instead, he got into the invention of a microprocessor, actually. Ted Hoff was involved in 4-bit microprocessor development and Intel Corporation. So that's a very interesting episode. This further, Memristor is a 3-terminal device. It's coming. Yeah, okay. And used for what is called the adaptive linear neuron, ADALIN, for least mean square algorithm. Yeah, M is missing, algorithm implementation. So this is ADALIN concept. So you say input, they are going through with some link and then added together. And then there is a training, and you train until error is minimized, and then you put the output between -1 and +1. So this shows some pattern. It's a 3x3 exercise. Pattern X is a +1, T is -1, etc., etc. But here, this is a memristor concept. It's a 1, 2, 3 terminal, and this is a chemical tube. So this is a sort of a controlling terminal where you control the conductance or resistance of this tube. So it's a variable resistance tube, but it's controlled by this third terminal, which was published in 1960. So that's for your reference. Again, back to memristor. So if you have a relationship between, say, Q and the phi, where phi is a function of Q in general, it can be curved like this. At any operating point, say Q naught, any operating point, if you take a slope, that slope is MQ, is memristance. This slope is memristance. So here is a smaller memristance. It keeps on increasing higher and higher, for instance, right? So that's a sort of a concept. And then back in year 2008, so that was 1971, and then follow-up paper 1976. Until then, no activity at all. I gave about Memristor once in a while when I taught undergraduate student or graduate student. So if you look at this chart here, can you see this one? Up until 2008, there's hardly any citation except earlier papers, few papers. For original paper by Leon Chua, and then follow-up paper in 1976. And I think we also had one conference paper. So maybe 3 or 4 papers. 2008, HP announced that they made the Memristor as a solid-state device. They fabricated the Memristor as a nanoscale device. But it was a generalized Memristor, not ideal Memristor. I will explain why. It turns out that the state variable here, V is equal to RWI, where W is a state variable as a function of W and I. So this is a current controlled memristor in this case, where W is a variable between 0 and this dimension D, separation between 2 plates, top terminal and bottom terminal of a device. This is nanoscale. And this is a doped region, is a W. So if a W is doped all the way, then you have a full conductance. If a W is undoped, it's a resistance, high resistance. So they have an undoped case. If everything is undoped, it's a R of high resistance. If it's fully doped, it's a W is all the way to D, then it's R on. It's a small resistance, for instance. So indeed, they did a measurement of voltage and the current. So they apply the current, right? They apply the current, and they measure the voltage, or vice versa. They apply the voltage, measure the current. But whenever input is 0, output is 0. See, this is a 0 crossing. Yeah. And what is happening in between is a W over D. See, W can be all the way up to 1, or W can be all the way 0, but it was between 0 and 1. It was oscillating between 0 and 1. So meaning that memristance was changing as a function of input. So if you plot the conductance, if you keep on applying this positive pulse here, conductance increase. And then if you switch to negative pulse, conductance decrease. See? Furthermore, they observed this number 8 figure. When they increased the frequency, it was becoming thinner and thinner. Eventually, at a very high frequency, become straight line, which was suggested in 1976 paper in Memristive device and the systems paper. So in fact, Stan Williams, who was a vice president of HP, he said they were inspired by 1976 paper. They made a device, but they didn't know what it was. After reading that 1976 paper, then they realized it was a Memristor. So they called Memristor found in their paper. So thereafter, this is important. After you have a solid state device, the number of papers increased drastically, almost exponentially. So by 2017, more than 30,000 citations, cumulative citations. right? So that was a main event. In fact, at the time, I was a translator to UC Merced. Leon Chua and Stan Williams, they called me, said, we found this Memristor, so we needed to have a workshop. So actually, let me see whether I have a, yeah, so I will explain that later. But what is exciting is following. When in HP Memristor, they have a top electrode and the bottom electrode, right? And then they have a sort of the oxide layer, doped and undoped. So if you look at this, see, you can see on the left-hand side, yeah, this doping is happening. So fully doped, so conduction happens. Now, if you apply this voltage negatively, okay, then it dissolves. So resistance becomes high. So again, when you apply voltage positively, see, there's a conduction formed. So that means the conductance is high or resistance is low. If you apply the voltage negatively, then it dissolves and then resistance becomes high. So that's the sort of switching principle of a memristor. In terms of fabrication of a memristor, yeah, you can make a memristor between top layer and the bottom layer, but you can integrate it with the MOS transistor. This is an MOS transistor. In the drain contact, in this via hole, they can make a memristor. See. Now, what is interesting is application. So as you can see here, you have a voltage signal comes in, it induces current through this memristor. And then you can have another input and then another current. They summed up together and produce even higher current, for instance, and then go through analog digital conversion and then output. So, and so thus you can have an array of memristors called the crossbar array that can be used for matrix multiplication type of things. So that's very important application, crossbars array. This shows analysis of memristor in terms of modeling. So you have a two platinum electrodes, top and the bottom electrode. And you have a titanium dioxide region, doped and undoped region. So this is axis variable here. So if they can have a titanium dioxide, or you can have a less than 2, for instance, x as a function of state. So if you apply the voltage across it here, depending on voltage duration, the W will increase. So if it increases all the way to here, when W becomes a D, then you have a full conduction. If you reverse bias it, reverse polarity, then it decreases and then becomes a high resistance. So you can say that the voltage is equal to resistance times current. Resistance is a function of a W. This is not Q. So this is a W, state variable. It's not ideal memristor in that regard. So memristance is defined by RW is R on W over D plus R of 1 minus W over D. So when W is equal to 0, for instance, then it's R off. When W is equal to 0, switch is off. When W is equal to 1, then this becomes 0. This becomes 1. It's R on. When W is fully on, it's R on. Yeah, so that's a low resistance state. When W is 0, high resistance state, R off. So you can see that this is a binary type of operation, either R off or R on. But W is in between, so you have many different kind of variables. And then W equation, dW dt, state variable is mu V, mobility, R on divided by D multiplied by current, for instance. So again, I emphasize that state variable here is W. So it's a generalized memristor. It's a rather memristive device, but later we decided to call everything memristor, right? So this is November 21, 2008. We held the first memristor and memristive systems symposium at Berkeley campus. I have to admit every time. So UC Berkeley campus, November 21, 2008. I organized this symposium, invited Stan Williams and Leon Chua. And there we discussed the crossbar array of memristors fabricated by HP team. And so that was the first of the Memristor symposium in 2008. And this shows the citations, right? By 2017, more than 30,000 citations. In terms of yearly publications, 2017 was that year alone was more than 1,100 publications. But since 2021, 17,300 papers published. Since 2024, this is a somewhat older figure, more than 11,000 papers published. So you can see that enormous number of papers are published. You see, it's exponentially increasing like this. So in fact, the editors, they complained that too many papers are submitted on Memristors. Now, there's a different kind of a memristor, also fabricated by HP. It's a platinum tantalum oxide. So platinum tantalum oxide and titanium memristor as fabricated by. So they have a platinum parallel line. On top, they have a tantalum and then platinum on top. And in between, they have a tantalum oxide. So this junction is memristor, see? So whatever this dimension is, that's what it takes in terms of silicon area or surface area. So if it's a 3 nanometer, then you have a 3 nanometer, 3 by 3 nanometer. There you have a memristor, very small. So in this memristor, that is the equation. It's a very complex equation. I is equal to this nonlinear function multiplied the voltage. So this is a sort of conductance, memristor, memristive conductance as a memductance, where you have alpha over V, is function of voltage also, multiplied with 1 minus exponential minus beta V, plus X gamma over V, hyperbolic sign, and then delta V. So this GXV is a memductance, memristor conductance. And the state equation, you have a dx dt is if voltage is positive, you have this nonlinear equation. If it's V is less than 0, you have this equation. So this is a highly nonlinear equation, nonlinear model for this particular memristor. This is John Strechen, who is now in Germany, State Dynamics and Modeling of a Tantalum Oxide Memristor, published in Electron Devices, July 2013, for instance. So again, this is a generalized memristor, not ideal memristor, right? But now we call everything memristor. This shows the characteristic, see? So this is a voltage positive and negative. So when you start, from 0, this current in the beginning, when voltage is equal to 0, 0, you increase voltage, then increase rapidly. When it reaches some set voltage value, then it jumps to this curve, stay on that curve. And then when you decrease it, it follow this, right? And then when it becomes a negative, it's a polarity, current is just a magnitude. When it decreases, it follows this curve here. And when it exceeds this set voltage, which is a negative voltage, it jumps to this portion. And if you increase, so sorry, it was do this and then follow this, and then follow this curve rather. Follow this curve, and then at reset, it sets to this value and repeat. So if you keep on doing it, again, increase, follow, jump here, and then follow, decrease, follow this, and so on. And then if it becomes negative, follow this curve, right? And then when it reaches a reset voltage, it jumps to this state. And then when you increase voltage from negative of minus 1.5 to positive, follow this, and so on. So, and this one is a measurement for different frequencies, 100 hertz, 1000 hertz, 5000 hertz, and 10K, for instance. And this shows the fluctuation when percentage. So there's some statistical variation. And this is what's called the crossbar array. So you have an array of nanowires, top and bottom. In between, you have a sandwich structure. So each brown one is a memristor, actually. That cross section is a memristor. So you have, in this case, it's 4 memristor, 4. It's a 4x4 array in this particular case. And then again, you have a Lissajous figure like this. Right? So this one has 2 distinct states. High resistance state and low resistance state, right? So in terms of resistive switching materials, you have a different material system in this particular illustration. Chalcogenide, when it is very well arranged here, it's called the state 1. It's a low resistance, in this case, low resistance state. If it is randomized like this, it's a high resistance state. So resistance is high. If it is an electrolyte case, when there is a bridge from top to bottom, full conduction, it's a low resistance state. When there is a gap, that's a high resistance state. Metal oxide case, like HP case, when there is oxygen vacancy indicated by white region all the way, then there's a low resistance state, right? And when there is a gap here, see, white is limited here. So this is like a W. W is less than 1, it's a high resistance state. When W is fully covering this distance D, it's a high conductance, low resistance state, and so on. So phase change between crystalline and amorphous is a phase change RAM, right? Between crystalline and amorphous. So this is like a phase change memory type of a thing. Center creation and analysis of metallic silver protrusion is a German selenide solid electrolyte memristor. And then right-hand side is like a TI memristor case. It turns out you can have many different materials between 2 plates, top bottom plates, titanium oxide, plus aluminum oxide, tantalum oxide, tungsten oxide, hafnium oxide, zinc oxide, silicon oxide, and so on. So depending on the composition of what is sandwiched between two metallic plate, you can have a different ratio between high resistance and low resistance. The higher the better, actually. And then number of stable states also. So there's lots of materials research that's still ongoing, and it's likely to continue until they find the true champion. And if you recall, I emphasize what Jack Kilby said. Integrated circuit is about low cost, meaning that the fabrication is easy to have a good yield. So that's why material system is important. If it is a stable material system, it's easy to fabricate, then lower the cost. Until then, there will be competition. Now, another application is a well-known Josephson junction device. It's invented at IBM. But if you look at the model of a Josephson junction two-terminal device, second model is involving capacitor, resistor. This one is interesting. This is a non-linear inductor. And then here is a strange thing. I is equal to B cosine phi multiplied by V. So this is a Memristor relationship. I is equal to conductance multiplied by voltage, but conductance is a function of phi, just like Memristor, right? So with the Memristor concept, this is a more relevant circuit diagram. You have a current, you have this capacitor, you have a resistor, you have a nonlinear inductor, and you have a nonlinear Memristor. So this is a new model in terms of R, L, C, and the Memristor. So 4 components to describe Josephson junction device, right? So interesting. Now, to simplify, this analysis and explanation, you can approximate PQ curve with a piecewise linear function. So in this simple explanation, suppose Q is varying between 0, 1, etc. And then suppose there is a breakpoint at 1, and at that point, this is a 10, phi is equal to 10, and so on. So you have 2 slopes, one slope and another slope here, right? So in terms of resistance, memductance, here slope is a 10, right? So you have a 10 ohm memductance here based on this slope. Here is another one, it's a 0.1, right? So this is a 0.1 ohm. So this is a high resistance, it's low resistance. So this is a 2-state Memristor. Memristor with a 2-state. In reality, it's a continuous curve, right? But for simple illustration, you can have a piecewise linear approximation. So it turns out that everybody using a USB. It's a very popular flash memory chip, but it has its own problem. Cannot be economically scaled below 10 nanometers. Retention time is rather poor. Fails after switching between 10,000 and 100,000 times. It's low speed. It's very power consuming, and information per decade you lose about 20%. So question is, can you replace that with a Memristor? It's a possibility. So people are working on it, right? The potential of a Memristor to replace USB. Can Memristor be volatile? Is it always non-volatile? The answer is yes, it can be volatile. Yes, Memristor can be volatile. Memristors are classified into 2 types, volatile and non-volatile. Volatile Memristor exhibit spontaneous conductance decay after the cessation of electrical stimulation, which is a characteristic of their behavior. They can also display volatile memory properties, particularly in applications like synaptic functions, so neuromorphic computing. So there we use memristors, but they tend to be volatile. The other interesting observation is, can you bias memristor with a DC source? Answer is no, actually. So this explains why you shouldn't bias this memristor with the DC. This is a phi q curve. So suppose q is equal to phi raised to the power of 3. So if you have this type of memristor, what happens when you connect a memristor across a battery? So this 6-volt battery, like a car battery, you connect to the memristor, you'll see that it immediately destroys this memristor. So this shows to explain why. Here, right, you have a phi q curve. Q is equal to phi q. So phi t is equal to, see, integration of a voltage, right? So initial volt phi naught plus between 0 and t, v tau d tau. But v is E, right? E, battery, E volt. And if you integrate, it's ET, it's time varying. It's linearly increasing with the time. If you put the cube here, and then if you take a derivative, IT is equal to dq dt. So if you take a time derivative, it's 3 phi naught plus ET square, and then E. So it becomes 3E parenthesis phi naught plus ET square. So this is what is happening. Whatever this phi naught is, you start from here and increase polynomially. As time increases, it becomes infinity, which destroy this memristor. So shocking truth. DCVI curve consists of only one valid point, which is origin here. So when you bias, you can bias at 0 point, right? Current voltage equal to 0, but not any non-zero value because it destroys memristor. Indeed, it's very easy to destroy memristor when you handle it. So you have to handle it with care. So how do you know whether the device is memristor? So since 2008 publication of HP's memristor in Nature, there are many such publications reporting device. So how can they claim their device is memristor? They don't even have analysis sometimes. They have just a measurement. So then experimental definition of a memristor is, if it is pinched, it's a memristor. So it has to pass through the origin, because whenever voltage is equal to 0, current is equal to 0. Whenever current is equal to 0, voltage is equal to 0. So that's Ohm's law. And this other thing is hysteresis. So you can have a strange behavior like this, but it has to pass through origin. Now, even in 1971, there was an interesting paper from Electrotechnical Lab, Mukodai, Tanashi, Tokyo, Japan, and then Nippon, Columbia Company. In their publication, Solid State Communications, they say letter 8 memory. See, this is an 8 figure, but it passed through the origin. See, they didn't know it was a memristor, but they reported this letter 8 memory. First hint of pinched hysteresis loop, but they didn't know it was a memristor. So there are many cases like that. This is a 2009 nano letter. This has it's 8 figure. This has almost 8 figure, right? See, this loop happens here, and the straight line loop happens here. Another 8 figure, but it has a strange characteristic. Here, etc. So many interesting observations here. Another one here is many observations. This is a 2003.
क्या कोई भी admit कर सकता है?
Right, 2000. So many observations. So from ideal to extended memristor, it's all called memristors. So ideal memristor is shown here. V is equal to RQI, DQ, DT is I. So that was original 1971 paper. And then you have a more generalized ideal memristor, generic memristor, extended memristor, and then whole memristor. So this now extended memristor is called memristor. Right? So for instance, extended memristor here on the left-hand side, it is a voltage control I is equal to GXVB, and the DXDT is a GXB, for instance. And then you have a generic memristor, ideal, generic memristor, ideal memristor. So started from 1971 paper and now. So there are many, many kind of memristors. So example of non-volatile memristors, RRAM memristors, metal oxide, titanium dioxide, tantalum oxide, polymetric memristors, conducting polymers, ferroelectric memristors, ferroelectric films, manganite memristors, perovskite manganite, spintronic memristors, spin transfer torque, STT, magnetic layers. So this is now this is a biomemristor, for instance. So you remember silkworm? If you silkworm, cut it and dissolve it, and then make a device like this, it demonstrates memristor characteristics. So there is an application of a silkworm. Using fabric, you can make memristors, and then you can have a wearable computing, even on costume, because silkworm is having memristive characteristics like that. See? Back in 1939, this boron, commercial boron crystal. So this is a boron crystal here. When they measure the VI curve, it has a Lissajous figure like this. It's memristor characteristic. Back in 1939. Early radio, Cat's whisker is here in dotted line here. If you do the measurement VI, it's also memristor like this. So it goes back. So this is a more general definition of memristor by Rainer Wasser. He's a professor in Germany. Redox-based resistive switching memories. So he has a memristive devices, which has a nanomechanical memory, phase change memory, PC RAM, thermochemical effect, valence change effect, electrochemical metallization cell is a redox-based switching here in red one, electrostatic ferroelectric effects, ferroelectric magnetic force tunneling, magnetoresistive memory effect, STT, MRAM, etc. So this is all in his definition. He's a material scientist. It's a memristive devices or memristors. So it's very broad in that regard. This shows emerging non-volatile memory devices. RRAM maturity is low, meaning it's not fully developed. Cell area is 4F squared, which is small actually. F is the minimum feature size. So if it's 3 nanometer technology, it's 4 times 9 nanometer square, so 36 nanometer square if it's 3D. Conductive bridge RAM, maturity is low, again, less than 4F square if it's 3D. And then this is a phase change memory, RAM. It ranges between 4F square to 20F square, it's larger. And then ferroelectric RAM, 12F square to 22F square bigger. STT RAM, there's a spin torque transfer RAM, 6F square to 20F square, etc. And then this is flash, 3D NAND, 2D no type of a thing. See, it's rather slow, 50 to 100 microsecond. But this is in nanometer square. In terms of endurance, actually what this best is ferroelectric RAM and then STT RAM, they are pretty good. 10 to the 12, 10 to the 15. Endurance is good compared to RRAM, CBRAM, phase change memory. In terms of power, energy, yeah, phase change memory 10 picojoule compared to femtojoule, so it's rather power hungry. STT RAM in that regard is 0.1 picojoule, which is good. And so it has all different kind of behaviors and features. Commercially, now you can buy Memristor from a Gnome company. Yeah, we in our lab bought many of them and built some hardware system. We destroyed through uncareful handling. It's very easy to destroy. So my students destroyed many, but you can buy whole package and then do that. So this is a Lissajous figure at the different frequencies and so on, and the VI curve, that sort of thing. Yeah, so this commercial low memristor. So you can buy ceramic deep package containing 8 memristors here in this package. The measurement, and then they also have a 32 deep, 16 memristors in it here. And then it's a packaged one and some simulation result and measurement result and so on. And then Memristor CAD is also available now. Both Cadence and Synopsys, they support Memristor simulation and verification. So there's a simulation tool, LT-SPICE, Cadence P-SPICE, H-SPICE, Verilog A, MATLAB, and Simulink, etc. So there are many, many models also available in the literature. So this, the Professor Biolek, he has contributed by presenting Memristor model. So he presented the H-SPICE model for MS model and the NB model, etc. And then did a simulate. Here Memristor, 11,000 Memristor simulation. If you use MS model, it takes 67 seconds. NB model is twice of that. 100,000 Memristor, 4,000 seconds, and etc. Yeah, and then some cadence toolkit. And then this is a spin transfer torque STT MRAM, and the orientation of a magnetic layer in a magnetic tunnel is modified by using a spin polarized current. So when you depending on current, the polarization direction changes, and it changes the state of a memristor. So this is further illustration. When current flows this way is one thing, current flows the other way is the other thing. So that's how they control this switching and resistance in that. But if you look at the compact model of STT MRAM, it's a physics-based model equation is rather complex. But if you simplify it, it becomes like this in red rectangle. Voltage is equal to R theta, it's a state variable multiplied by current. R theta resistance is 2 RP 1 plus TMR, some ratio, over 2 plus TMR plus TMR cosine theta, for instance. So see, this is the state variable theta, ms d theta dt is equal to this nonlinear function. So this is a memristive device in that regard. So V is equal to resistance times I, where resistance depending on state variable theta, where that state equation is described by this highly nonlinear function. So in that regard, this is a generalized memristor, thus memristor, and this shows a hysteresis curve for that STT MRAM. So memristor and the non-volatile, not all memristors are non-volatile. A non-volatile memristor theorem 2 implies infinite, meaning that if a passive memristor exhibits 2 stable memory states, then it has a continuum of a stable memory state. So yeah, although we approximate two-state memristor, it's in principle there are very, very many infinite number of memristive state in that regard. Fundamental memristor memory theorem: all passive non-volatile memristor are continuum analog memories. And then the other interesting point is how are we doing with the time? I may be 26. Yeah, maybe. The other interesting thing is frequency dependency. So this shows the Lissajous figure when input voltage is sinusoidal at different frequencies. For instance, when it's 0.5 hertz, this is a blue curve like this. And then when it's 10 kilohertz, it's dark black. So that's a short, almost a straight line here. And then in between 1 kilohertz, 500 hertz, 100 hertz, 10 hertz, etc. So in other words, if you approximate resistance, high state, low state, for at different frequency, it changes. So when frequency changes, say 0.5, G off conductance when off state, and the G on state 1.15 millisiemens, and when it's on 11.4 millisiemens. When it's 1, 1.3, 10.8. When it's 10 hertz, 1.4, 8.4. When it's 100, 2.3 and 7.6. All the way to when it's 10K, 1.7 and 2.1. So see, shrink, the difference shrinks as a frequency increase, because at infinity it's supposed to be one straight line and it will be same value, right? So you can see that for different frequency, your conductance value changes, right? On, off is different. So this is blue is when it's on state, off is off state at the different frequencies. So you can convert for instance, the matrix information, say 1/16, 1 to 1, 2, 4 to 1 to 1, into frequency component like this. So then you convert this input data into frequency component. Then you can do convolution filter experimental setup, convolutional filter, image processing, 2D convolution, Gaussian blurring, hardware 9x9 crossbar array, and then input 128 by 128 red, green, blue, 8-bit unsigned representation, pre-processing, 8-bit RGB noise, etc. Input voltage luminescence of 256 linearly mapped to amplitude of 0.15, 0.66. Convolution and the output image 126 by 126. So you can apply this by using frequency characteristics, original image, and input image, output image, using this convolutional filter technique. So yeah, original image is clean here. And when you code with the frequency information, that is a representation here. And then output filtering is a represent. So it's not as clean as the original image here, but it shows the principle that by doing a frequency coding using Memristor characteristics, you can get a decent output. Yeah, so this shows expected versus measurement. Measurement solid line, dotted line is expected value, and there is a pretty good match between red component, green component, blue component. So this is a novel application using the frequency dependent characteristic of a Memristor. So you can code input according to the frequency, and then to the filtering, and they get the output processing using Memristor, for instance. This again shows Memristor operation resistance switching. We showed earlier, and then that's a cross-sectional cut. And then the different characteristic of RE RAM, phase change RAM, magnetic RAM, STT RAM, and then again this is a different cut. Is somewhat earlier, 2013, in terms of density, right? And then see, Memristor is like a 4F square with STT RAM, magnetic, yeah, a spin torque transfer is a 20 to 60, so it's a significant increase. Phase change memory is 4 to 16, right? And the energy, Memristor 0.1 to 3. This one is a 2 to 25. STT RAM is good in that regard, 0.1 to 2.5. Read time, less than 10 nanoseconds. Phase change memory 10 to 50 nanosecond. Write time is about 10 nanoseconds. This one, phase change memory, takes much longer, 50 to 500 nanosecond. STT RAM, 10 to 90 nanosecond. Retention years. Endurance, 10 to the 12, 10 to the 9, 10 to the 15, right? So there are competing technologies. There are some successful startup companies using this Memristor. There was also an attempt to produce a real ideal Memristor using real magnetic flux. So it's called a Phi Memristor, real Memristor found, not ideal Memristor, but not generalized Memristor, so real Memristor found. So they had this paper, Journal of Applied Physics, in 2019, submitted May 2018, accepted January 2019, published February 2019 by Frank Wang, Ling Li, and then they also invited Leon Chua to be co-author. So they did an interesting measurement. So this is a Memristor here. It's rather bulky, right? Core Memristor. And they did a measurement, right? Induced voltage and the current, etc. So continuous range of resistance, here blue, and this is a, here is a current, and this is a blue is a voltage. So you can see that although current is almost constant at 1 megahertz, as time goes on, voltage is decreasing, meaning that resistance is decreasing over time. 1 megahertz, this is IT, voltage is also decreasing like this. So they showed some interesting characteristics. They introduced a model like this. Phi is equal to hyperbolic tangent, and then inverse hyperbolic tangent, etc., which is a function of Q, right? Q is here. So phi is a nonlinear function of Q, so Memristor characteristics. And then they did a measurement, IB measurement, which is a lot rather, almost linear here, and then set voltage and reset voltage type of a thing, 2 megahertz and 4 megahertz, right? And they did publish, but later they withdrew this paper because physically was not fully justifiable. It was working only for square pulse, not sinusoidal, and so on. So they withdrew. So was almost there, but was not really there. But I just put this one as a reference, demonstrated for square pulse input only, and it was not really clear whether it was functioning at non-square pulse. So they withdrew this paper, right? But this is interesting. They thought that they found the few memristor, but not yet. Memories and let's see. Non-volatile memories. So comparison key attributes between mainstream memories and non-volatile memories. So SRAM, DRAM, flash, phase change memory, RRAM, MRAM, SOT, different kind of Ferro RAM, FE RAM, etc. So this for your reference. We discussed some already. So yeah, so they compare cell area, the voltage used, and then read time, write time, right? So you can see SRAM is very good in terms of speed, 1 nanosecond range. So for speed performance, SRAM is still used a lot. And then endurance, 10 to the 16, 10 to the 16. Flash is 10 to the 5 only. NAND is 10 to the 3, 4. It's very low. Phase change memory 10 to the 6, 10 to the 9. RAM 10 to the 3, 10 to the 9. It's not mature, etc. So that's the thing. So last lecture, people ask about emulation, right? Memristive emulation. So this is one example of emulation circuit. Some a diode bridge with a capacitor, and then they emulated some aspect of Memristive, although not perfect. But Professor Ranjan, I think, will have a lecture on emulation. In the first lecture, I said, can we increase the number of components using memristors to reach the state of a human brain, mimicry of a human brain? So that's where neuromorphic computing is ongoing. So synaptic weight is used a lot, but more recently, people are extending that synaptic connection to dendrocentric learning AI. So this is a more involvement. So dendrites, there are many dendrites besides synapses. So that is ongoing effort. So the Professor Bohan at the Stanford University is leading this effort. Dendrocentric learning for synthetic intelligence, as published in December 2022. And so this is sort of the one snapshot. Essentially, you want to reduce energy. So you have a dense 2D array, dense 3D array, sparse 3D array will approach eventually human level. And number of neuron is like almost 100 billion neuron level. And in order to do that, you need a sparse 3D array rather than dense 3D array. And for that, they are emphasizing dendrocentric learning AI, so which is yet to come, but just for research interest, yeah, people are looking into dendrocentric learning AI. Also new material, 2D material systems. So that is also active research ongoing using 2D material systems. So that is for your reference. And that is pretty much today's lecture, but now we can have some discussion. So I entertain your questions. Thank you.
Okay, from the attendees, if you have any question, you can ask Professor.
Good morning, sir.
Good morning.
Sir, I have a question.
Yes.
Actually, you described about team memristor by Sahar Watinsky. Actually, why this team memristor is used only for logic operations? In almost all the papers, for logical operations, these team memristors are used. Why not other models of memristors not used?
Which one? What is a team memristor? What is a team memristor?
Yeah, team memristor is used only for logical operations. In most of the papers, for logical operations, these team memristors are used rather than other
okay. Yeah, yeah.
memristors.
That's
Other,
a model.
yeah, why
but,
is the reason?
Yeah, it's based on the team, TEAM. Yeah, team memristor. So it's mainly work of the Technion people's effort along with the E.B. Friedman at the University of Rochester. But there are other memristors. For instance, there are group in Europe and other places using a different kind of memristors. So Strachan, I mentioned earlier, he's also working on different kind of memristors. So that's one example. Yeah. Any
Good morning.
other question? Yeah.
Good morning, sir.
Yes.
Sir, you have discussed one thing, that is Hodgkin-Huxley model.
Yes,
Here,
Hodgkin-Huxley.
yeah. So that is one is for potassium channel, another is for sodium channel.
Yes.
Sir, so then in potassium channels, you have considered only one state variable, that is N.
Yeah.
But in the sodium channel, there are two state variables, that is M and H. Then what are the significance of, sir, these two, means the variables that have chosen in both the equations?
Right. Yes. So this is very complex system, and this NMH, they are fictional quantities. They're actually probability functions, NMH, and I do not know how they come up with this model, but in principle, when four elements are vertically aligned perfectly, then there is a penetration between inner wall of a membrane and outer wall of a membrane, so conduction. So that's alignment, so over 4. So when n is equal to 1, then it's n4 is 1, so perfect conduction. And the other one, n and the M and the H, which is involved in sodium channel, yeah, that if you look into this, there is some local activity and the negative region and so on. So it's a little bit trickier, and that turns out to be very important function. So recently, Professor Chua and Professor Alon Escoli and Professor Fernando Corinto at the Torino, they've been doing what is called the edge of chaos theory using this Hodgkin-Huxley model in the region where this the resistance IV curve is a negative slope. So the getting M and H involved in this complex function in DC characteristic, there is the local activity region. So that's sort of a tricky part, and it was almost a genius for Hodgkin-Huxley to come up with this model. Yeah, so it's a very, very complex. So it's a very exciting equation, but on the other hand, you cannot build the memristor circuit using this model. It's too complex. You cannot do that. But there are some other inventions being made. Stan Williams at Texas A&M now, he is developing new kind of memristors with local activity and so on. So later on, when we discuss neuromorphic computing using memristor, we'll discuss that. Yeah.
Okay, sir. Thank you, sir.
Other questions?
Hello, good morning, sir. I am Sachin Tiwari. Hello.
Yes, go ahead, please.
Sir, recently I read an article about the mem transfer. So there is any difference between the memristor and mem transfer?
What is it? Mem plus, I'm sorry,
Mem
what is it?
mem
Mem,
transfer. Yes, sir. Uh, Sorry, sir. I also write my question in the chat box. Mem transfer.
let's see. How do I read the chat box? I saw chat box.
It's mem transfer he is writing. Dr. Sachin Tiwari is writing mem transfer.
Yes, sir.
Mem transistor. Yes. So now the mem transistor is like a 3-terminal memristor type of a thing. It's more closer to the memristor of withdraw and half type of a things. But yeah, it's a 3-terminal device. It's different from 2-terminal memristor. It's more active thing, and people are also extending to photonic devices. Yeah, photonic memristors and so on.
Okay. Thank you, sir.
Yes. So yes. Okay. Sorry, I didn't catch it earlier.
Sir, there is one more question from the Abdul Basit.
Yes.
He is written in the chat box. Actually, it's a long question. Leon Chua originally predicted a direct relationship between magnetic flux and charge, which led to the introduction of the memristor.
Right.
However, in most research papers, the characteristic spin hysteresis loop is typically observed between voltage and current, which are
Right.
in fact time derivative of flux and charge respectively.
Right.
Recently, I came across a paper on a MEM transistor actually, emulator, that presented a pinch hysteresis loop directly between flux and charge. The authors argued that while the memristor is an advanced or extended version of a resistor, it is the MEM transistor that truly represents the flux-charge relationship. Chua initially proposed this. I found this argument compelling and the concept of the MEM transistor to be a more direct realization of Chua originally theory. What is your opinion on this, sir?
There has been a heated discussion in early stage whether that was physically ever possible. I give credit to Leon Chua's concept because essentially it's a 2-terminal device. So it's just like a resistor, capacitor, inductor. It's a 2-terminal. That's a main difference between memristor and the memristor. So in my view, mem transistor is like a memristor. It's closer to memristor. And, they can explain this phenomena using charge, that sort of things. But real original concept is based on 2-terminal device. And I think a 2-terminal device is important, especially to build a circuit. So I think there is an application of MEM transistors. Why not? If you can use it, should use it. But Memristor itself, its merit is like a crossbar array where you have a very simple structure of interconnect and so on. If you use MEM transistor, yeah, it's interconnect becomes a little more complicated. On the other hand, to prevent some leakage current type of a thing, you need a MOS transistor. So you have a 1T 1R type of configuration, which requires additional terminal. So you can argue that yeah, if you use a MEM transistor, maybe you have essentially same number of terminals. So it may have its own merit. So I wouldn't exclude that possibility. I think it's a novel idea and can be exploited also. So I welcome such a addition. And what is really important is a solid state concept. And today's integrated circuit, and why not? If you can have a solid state functionality, I think it's good.
Okay, sir. There is another question from Harshada Suresh wrote, is there any relationship between memristor, mem capacitor, and mem inductor? Also, are mem capacitors and mem inductor as important as the memristor?
Okay, so this is it. There are some interesting application of a mem inductor and mem capacitor type of a thing, but in my view, application domain may not be as broad as a memristor. Yeah, so one of the key component of a memristor in neuromorphic computing is a MAC operation, multiply accumulate operation, which we will discuss when we have a neuromorphic computing. That is huge. There's lots of matrix multiplication, but using memristor crossbar array, you can have a very energy efficient analog computation. To me, that's a huge advantage of using memristor array.
Is in the chat box, how mem capacitor implement physically, from Praveen Jarande.
I do not really know, but there has been some emulations for the mem capacitor and so on, but I haven't seen the physical entity myself.
Okay. And what characteristics should we consider for designing a mem inductor? Another question is this.
There was an interesting application of a mem inductor in the learning mechanism where amoeba movement, actually the people composed that one was originally proposing that one. Amoeba movement is a temperature sensitive, and in that type of a circuit you can use mem inductor to replicate what is happening with the amoeba in sense of environment, ambient temperature type of a thing. Yeah. So in the learning like a temperature sensitivity type of a thing can be captured in a MEM inductor application circuit. But there has not been very many applications published yet. Maybe people can find some. Any other question?
Yes, sir. There are a lot of questions from the attendees. Actually, your session is so much important for us. Actually, that's why they are asking question. If you feel we can end this session, otherwise we can take the question from the attendees.
Maybe we can take a couple of more questions.
Okay, sir. Which question? Sir, while implementing memristor-based hybrid logic circuits like memristor ratioed logic and memristor threshold logic, whether the memristor behaves like a resistive switch. What is the role of memristor with CMOS rather than resistor?
Well,
shall I repeat the question, sir?
Yes. No. So the beautiful part is you can program resistance digitally. We will show that you can change this. See, memristor has many state, right? In fact, people working on device, Joshua Young and other people at the University of Southern California and his colleague, Professor Shah at the University of Maryland, Amherst, they demonstrate that you can have 1,000 stable state in memristors. So, getting there, you need a careful peripheral control circuit, but you can have many different stable operation point, which allow you to program different conductance values or resistance values of a memristor, which you can digitally control. That's huge. So you can have a programmable analog circuit using memristor. Whereas if you have just a resistor, you cannot just go in and then change resistor. But memristor, once it is there, you can program. So you can have a programmable voltage amplifier or different applications, or even neuromorphic computing. You can program after learning different conductance values in a Memristor array and use it for inference and that sort of application. That's a huge, that's a huge application.
Okay, sir, there is another question. What characteristics should we consider for designing a MEM inductor?
I cannot give you really, I do not know too much about MEM inductor. So sorry, you have to do your own search for that. Yeah.
Okay, sir, can you use ferroelectric materials engineering to control memristor device variability?
I'm sorry, can you repeat the question again?
Yes, sir. Can we use ferroelectric materials engineering to control memristor device variability?
That's a possibility. I wouldn't rule out any other. So this is always a big question. What about the variability? What do you do? How do you overcome that? So the best way is to have a process control, but in nanoscale may be difficult. So then how do you overcome this thing? So there have been a very novel research approach, how to maintain accuracy by using multiple, memristors. So Professor Alex James, for instance, his group is looking into that. You have a multiple memristor configuration, and use that as a a device to control the precise memory resistance value and so on. So yeah, so the best thing is whatever you can do. So one example is in analog circuit, you also worry about variability and so on, but you use a digital circuit to tune it. So I would think that similar thing can be done in memristor circuit, but that includes some increased overhead of digital circuitry. And for that, you may need a CMOS to do that sort of things.
Okay, sir. Thank you very much for your clarity on the attendees' questions and for your thoughtful knowledge about your memristor devices. And we will continue tomorrow with your lecture at
What time
9.
would it be? Tomorrow, what time is it?
Same time, sir, 9 a.m. IST. Your time will be, yes, your time will be 8:30 PST there.
Okay, sure. All right.
Okay.
Okay,
Thank you,
thank
sir.
you. Thank you.
Thank you,
Bye-bye.
sir. Bye-bye, sir. And all the attendees, please be ready for the next lecture, which will be held at 12 p.m. 12 p.m., which will be taken by Professor Rajiv Kumar Ranjan, sir. And you can ask your queries there also if you want. Okay. Thank you. Hello. Actually, the time, if you are listening, actually the time for the next lecture is 11:30 p.m. 11:30 a.m. Sorry, and just follow the schedule which is provided to you. Group में message डाल